Okay, so thought I'd just start with this is what we're aiming for. This is what it's going to look like. But we'll delete it all or most of it, and then I'll build it up again. So let's delete the graphs, and then just delete everything in here, and delete all these. Okay, so first of all, let's put our time in. So 0, 1. Then we can click and select those two, hover over the bottom right hand corner so you get the square. Then if you just click and drag down, I've gone to 100 seconds here. Great, so now we're going to put in our rate constants for the forward and backward reaction. So remember, these are rate constants, not equilibrium constants, but they are very much linked. So the rate, let's just put them as 1 and 1 for now. The equilibrium constant is actually going to be the forward rate constant divided by the backward. So I've got to put equals. I'm going to make it do the sum for me. That, click on it and then press slash divided by that. One is just check that. So if I put 2 in there, that changes to a half. Okay, that's fine. Let's leave that as 2 actually. Time stretcher, right? This is basically just a little number that is going to stretch our graphs in the x and in the x direction. It's just a little bit of a fudge factor. Concentration of A, so we'll just put a starting value of 100. These are just numbers just to make sure we can see that our formulas are working. Let's put concentration of B as 50. Loss in A, we'll come back to this in a bit. Let's just put 0 and 0. That's going to be for if we want to demonstrate if things are escaping from our system, if it's not a closed system. Okay, so concentration of A, the very starting concentration of A, I want to be this number up here. So I'm going to press equals, and then I'm going to press that. And this one, similarly, I'm going to press equals, and then I'm going to click on the concentration of B there. Now it's gone a color because I've got some conditional formatting on there. So let me just delete all the conditional formatting from there. We'll put it on later. Clear rules from entire sheet. Lovely. Okay, so the gain in B. This is going to be so the rate equation of the forward reaction is the rate of the forward reaction equals K times the concentration of A. So we're just going for a really simple example here. So I'm going to put equals the concentration of the forward reaction times by K forwards rate constant of the forward reaction. Now, crucially, I want that red box to always stay there. So what I do is I press F4, and that makes some dollar signs for me. Like that. So $B, $1, and that means it's totally locked. So when I drag it down later, that box will always stay there. And I'm also going to have this time stretcher in there and do the same thing. So lock that. Cool. So my gain in A, well, that's the backward reaction. So that's the rate constant. The rate equation for the backward reaction is K backward times the concentration of B. So I'm going to put equals. So K backwards, I want to lock that, times the concentration of B, just that one. I'm not going to lock that, and then times our time stretcher. I'm going to lock that. Locked. Great. Now, my loss in B is actually going to be the same as the gain in A. But the reverse sign. So anything that I lose, anything that I've gained from A means I've lost that exact in B, because all of our stoichiometric coefficients are 1. So I'm just going to put equals minus that. Similarly, the loss in A equals the gain in B. So I'm going to put equals minus gain in B. Now the change, or the change, let's change that, in A is going to be the gain in A plus the loss in A. Now actually we'll put our loss A thing in here. So I'm going to put no, I'm just going to keep that as that. Similarly, my change in B is going to be press equals gain in B plus loss in B. Now, actually, just the way that these numbers have come out, it's showing that's 0. So I think that's because I've got some funny, yeah. So there we go. It's looking a bit better. Now Q, this actually we know our expression for the equilibrium constant is the concentrations of your products divided by the concentrations of your reactants. But you can work this fraction out when it's not at equilibrium, and people tend to call that Q. So I'm going to put Q is equaling the concentration of B products divided by the concentration of A. Cool, so crucially that's not the equilibrium constant because it's not at equilibrium, but we still worked it out. Now, yes, crucially, I need to work out the new concentrations of A and B based on what's happened this second. Okay, this second has elapsed, and I've gained 0.5 of A and I've lost 0.5 of B. So this new concentration is going to equal the old concentration plus whatever the change in A was. Okay, so actually the concentration of A has gone up. Similarly for B, this is going to equal the old concentration of B plus whatever the change in B was. Concentration of B has gone down. Now I'm going to select all of those, and if I get my magic cross, drag that down. Now Excel has done something very, very clever. So anything, so let's say that was there, the red box is there. Because I've dragged it down, if I go to the bottom, the one below it, the red box is now there. Okay, it's dragged the value that it's using down. Crucially, anything that's dollared, so the blue and the purple box, they've stayed the same. Okay, so now I can take that whole row and I can drag it down, and it keeps on doing the same sums. Okay, so we're nearly there. We want to plot a graph now of concentrations against time. So I'm just going to select all of those, go to insert, and just get a scatter graph in there. Looking good. There. Okay, so let's just see if that's working. If I change this to 500, okay, yeah, stuff's happening. If I change the rate constant for the forward reaction to 5, okay, yeah, lovely, stuff's happening. Right, so that's a really nice graph of concentrations on the y-axis and time on the x. What would also be nice to have is time on the x and rate on the y-axis. So it's a little bit more complicated. So I'm going to click and drag on the time. Now I'm going to press and keep pressed the control button. So our rate of the forward reaction is equal to the gain in B. So I've got control held down. I'm going to hold down control again, and I'm going to select the gain in. I can just do them at the same time, couldn't I? So I've got those selected now. If I go to insert, chart, scatter. Right. So some interesting things happen here. Something that the students often get confused by is do the lines meet? Should the lines meet? And the answer is it obviously depends on what the y-axis is. And we see here that the graph of concentration against time, the lines don't meet and the graph of rate against time, the lines do meet. And we can obviously explain that to the students. And one of the conditions of dynamic equilibrium is that the rate of the forward reaction and the backward reaction are equal at equilibrium. Now, the concentrations of very, very strange scenarios do meet, and you can prove that here, where the rate constant of the forward reaction is exactly the same as the backward reaction. Therefore, our equilibrium constant is 1. And then if it is just a straight A becomes B and B becomes A, then they will meet. And no matter what I have my starting concentrations, they will always meet. But that's really rare, almost never ever happens. And normally the rate constants of forward and backward reaction are different. And in those cases, these lines don't meet. But this line will meet. Or these lines will meet. Okay, so let's get a graph of Q against time. So we're going to select our time, then hit Control, keep Control pressed, and select Q. And then we can insert that. And we get this. Lovely. And we can see that it's changing very quickly at first, but then it converges on, lo and behold, 0.3333, which actually is the ratio of our rate constants for the forward and backward reaction. Okay, so and if I change this to 6, we see that has changed to a half, and if we go down to my graph here, yes, this is converging on a half, and I can see that here. Now, if you want to, you can add some conditional formatting, so I can compare the those don't end up as the same color, and that's just showing, it's another way of showing really that our lines on this graph haven't met. Whereas if I select the gain in A, there's a gain in B, so that's sort of a proxy for our rate of the forward and backward reaction. We get conditional formatting on that. We see that although they start different colors at the first, they will always converge on that same color. The loss, did we put it in? Let's see. No, so we haven't put it in. So gain in A. So if we actually change that, do we add a term? So we've got minus this loss in A. Actually, let's do this on change in A. So over here, let's put minus that, and then let's put this one as minus change in B. Okay, so and then of course we need to make sure that all of it goes, that follows all the way down, and it's totally died. I know what I've done. So I didn't lock it, silly man. Here we go. So if I go to lock that, and if I go to lock that, this is a nice sort of that kind of problem solving and finding bugs in your own work. There we go. Now that's working. Okay, so at the moment we're not losing any A. It's a closed system. But if suddenly I let some A sneak out each time, let's say 3 sneaks out, then you can see straight away that my graphs start to go a bit funky. If I make a little bit more escape each time, whoa, some strange things are happening, because suddenly our rate lines are not meeting, and they look like they're never going to meet. And that is because, well, you know, you can obviously chat about this with the students and ask them for their thoughts. But normally, if you make some B, so i.e. the forward reaction happens, the forward reaction gets slower, and the backward reaction actually gets faster, because you've made more of the products ready to react backwards. If you start losing things, then that doesn't happen. You don't get that quickening of the other reaction. because the stuff's floating away. And actually, we could obviously use that and do use that to our advantage when we want a reaction to produce all products. If we remove those products as they're made, a Harvard process classic example, then it, inverted commas, pulls the reaction over, and we keep getting the forward reaction happening and not the backward reaction, simply because you're removing the actual particles to collide to make the backward reaction happen. Yeah, so and if we can lose some B, and you think that might help things if we lose B as well as A, but actually it turns out it doesn't. It makes it even worse. But yeah, just a really nice example of how we can build. Oh yeah, and we definitely don't see it converging on an equilibrium constant. Perhaps if I make it a little less extreme, let's make that back to 0. Yeah, this is quite nice, and we can see that it's not looking like it's converging on an equilibrium constant, which is what it will do when we have a totally closed system. Cool. Well, I hope that has been helpful. Happy simulating. Simulation is obviously incredibly powerful and provides a really neat way to get some immediate feedback from seeing what happens if that question that we should always really be asking ourselves as scientists. What would happen if I did this?